Grade 12s, this is our very last module of chemistry for the whole year. I'm quite excited about this. Hopefully you're excited also to be pretty much done and wrapping things up. So this is module 32 and we're going to cover titration curves and we're going to put it together all of the things that we've learned about strong acids and strong bases, weak acids and weak bases, and we're going to look to see what the pH would look like on an actual curve, like if you were to graph it while you're doing a titration. So this is what we would have done just before you got ready to do your final lab practical. This may be a little more complicated than what you were going to do. You're basically just going to standardize your base, figure out what concentration your base was. Does it jive with what the concentration I would have given you would have been? And then you would have tried to figure out the concentration of the acid and what the percent difference would be from what it should be in theory to what you would have gotten in the lab experimentally. And the acids that I would have let you use are ones that are pretty stable at room temperature. So you would have gotten pretty good percentage of air. In other words, not very much percentage. Most people, when they do the lab, they get less than 1% air, which is exceptional. And it also means that you did your technique properly. So everything from using the pipette to cleaning the glassware to reading a burette to being able to just overall understand your stoichiometry calculations, that's really sort of what I wanted you to be able to take away from the course. So I hope that next semester when you're at university you get a chance to do a titration. I hope that you can do it in person, and if not, at some point in your career you can definitely have a chance to do it. It's one of the basic chemistry labs. Okay, so let's go over a couple of concepts. If you need to review any of the terms or you want to look at the process again, go back and watch one of the other videos. But just let's get set up as to what the terms were called and basically how to do these calculations and what the graph looks like. Okay, so here we go. Note that the word burette can be spelled two different ways. Tomato, tomato, do it however you'd like. I think one's the English version and one's the Americanized version. That was our long, skinny glass tube with the stopcock, the valve at the bottom, and then the tip. Okay, so what do we remember from this? We would remember that it's called a burette. You remember that you always read the burette to 2 decimal places. You'll remember that it starts at 0 at the top and goes down to 50, so that when you're doing an initial volume measurement and a final volume measurement, you always have a smaller number first, a bigger number second, so the change in volume is the final minus the initial. You'll get a positive value. That would be one technique tip to remember. Once you've added in a specific volume of either the acid or the base, that's what it shows here. Then you call whatever it is you're putting into your Erlenmeyer flask or your beaker as the standard or the titrant. Okay, it's interesting here in this diagram that it shows you could put 2 burettes set up on a burette stand, like a burette clamp on a retort stand, and you could do that because what if you just wanted to dispense a certain volume of that acid into the Erlenmeyer flask? Well, then you wouldn't have to use a pipette. You could dispense a specific volume. So in this case, we have a volume of 10.00 milliliters that was dispensed using either the burette or a volumetric pipette. We know the volume of this. We don't know the concentration. Okay, so what do we know about the base? Well, we certainly know what the base is. We just don't know the volume that's needed to be used until we do the titration. And then, like any stoichiometry problem, you have 3 things that you know and 1 that you don't know. Basic stoichiometry to figure out how many moles, mole ratio, and then from the mole ratio, use your molar mass to get your concentration. Okay, all right, so here we go. We know our volume. Now in this case, our standard or the titrant is a base going into an acid. So if we use phenolphthalein as our indicator, then I want you to think about what the color is going to look like. Well, we've added phenolphthalein to our Erlenmeyer flask that has acid in it, so it's going to be colorless to start with. As you drop the base in, this time it's going to go to the fuchsia color, right? So our end point is when it's going to be our neutralization. That's when the solution goes from colorless to pink and it goes slightly back to colorless. That's going to be when you're going to be done. Okay, so a couple of things from down below. What do we call this? We know this is a titration, a procedure to accurately measure the volume of a solution that has a known concentration. We call that the titrant or the standard, and we use that to figure out what the unknown concentration of the solution is going to be. Okay, the most typical type of titration is an acid-base titration, and that's basically all we've done from grade 11 and grade 12. You learned about neutralization reactions way back in grade 10, and we just keep building on that information about acids and bases. Does it get more complicated? Yep, of course, and you can wait till you get to university for that. Okay, what do we call this thing? The equivalence point, and how is that different from the end point? Your equivalence point is when your moles of hydrogen ion equal your moles of hydroxides. Experimentally, when we do this in the lab, we're looking for the end point. So the end point is really the equivalence point, but we've used an indicator to tell us that that's when the equivalence point is. Okay, so yes, it's the same thing, but we just call it the equivalence point, and we've used an indicator to tell us that it's the end point. Okay, the key thing about the end point with good technique though, you want to make sure you choose the right indicator, and I'll give you some tips later on in some of these questions. All right, next, what is a titration curve? Well, a titration curve is a graph. Volume of the titrant added and the pH of the solution. Okay, I'll show you the graph on the next page, and then I'll explain a few things you can get, because you could get data from a pH graph, right? From this titration curve, you can see when the end point is, and from that graph you can read what volume you would have used in order to reach your end point. Okay, so you could do this in the lab using a titration, physically, using the burette setup, or you could just read it from a graph, because the graph will show you where the end point is, and then you can read from the graph the volume of the standard or the titrant that you added in. Okay? Last, you want to remember about this hydrolysis of water business, because we want to remember that a Bronsted-Lowry acid is a proton donor and a Bronsted-Lowry base is a proton acceptor. You will get the hydrolysis of water. There's my water molecule again for the last time before I put them away. Our water molecule, right? You're going to look at the salt that gets produced. What was that conjugate to any of the weak acids or bases? They produce a strong conjugate. It's going to act like that conjugate acid or base and pull apart water, okay? Therefore, you are either going to have left in that solution some excess hydroxide ions or some hydrogen ions, and that just means that your equivalence point is going to be in the acidic range or the basic range, depending on how that hydrolysis of water goes. We'll do 3 examples and you'll be able to get it a little bit better. Okay, so how does it work? Here's that example that we've done for the last couple of lessons. If you have a weak acid, strong base. Acid base gives you a salt and a water. Let's look at the salt that gets produced. Now I want to think about the dissociation of that salt, and then I want to link together. Let me just change the color here for a second. I want to link my weak acid to its conjugate. Remember what's going to happen? It's like its partner. What does the weak acid turn into after it acts like an acid and is a proton donor? You are looking at the CN with a 1 negative charge. Weak acid, strong conjugate base. How does that conjugate base, because it is strong, it's going to be able to act like a base, proton acceptor, and it's going to hydrolyze the water and form excess hydroxide ions. Okay, what's the extent of the hydrolysis reaction? Well, we can figure that out because we know that Ka times Kb gives you Kw. Weak acids will have a small conjugate or small Ka value. Strong bases have a very large Ka value. Based on the formula, we know that the Kb of a conjugate of a strong acid is going to be very small, and the Kb of a conjugate of a weak acid is going to be very large, right? So what's the trend? The weaker the acid, the greater the strength of its conjugate, and hydrolysis occurs to a greater extent. This page, if you are lucky to have a printer print this page, this is the only page that kind of summarizes it all. And if you just have to make a summary note, this is the one, okay? 3 important pages from the whole unit. This is the third one, right? The other one was the pH calculation page. And the first one, I can't remember the top of my head right now, but it was one we did in the first week, that module on the Friday, okay? So here we go. Let's look at this, which is called a titration curve. So a titration curve shows you the volume of base. This was our titrant because it was in our burette right here. What volume of base gets added and what's the pH? Okay, so there's a few things to look at. The first thing you notice here is that we're using acid and bases where we're using a weak acid and a strong base. Okay, you'll notice that it will change color, the equivalence point. Can you see that on the graph there? Where the moles of the hydrogen ion equal the moles of the hydroxide ions from the acid and the base is at a pH of 9. Can you see how when you look at that graph, you basically look at the graph and see where on that graph do I get that change? Okay, you get the change at a pH of 9, so you read that from your y-axis, and then you do ... go all the way down, and that will tell you the volume of the base that you added in. So you see how you can do a titration question without having to do the actual lab? Being given some data, okay? This is what that titration curve looks like. Now, let's explore a couple of things on this graph. Remember, this is always going to be the option where you've got a weak acid and a strong base. Your equivalence point is going to be in the basic range. Why is it at a pH of 9? Because of the hydrolysis of water that's going to take place because you had a weak acid, produces a strong conjugate base, it acts like a base, proton acceptor, you're left with hydroxide ions in that solution, and that's what translates into a pH that's alkaline. Let's show the work. Here we go. Here's my neutralization reaction. I've got a weak acid and a strong base. Great, gives me a salt and a water. Now, let's look at that salt, the dissociation of the salt, because which ions am I looking at specifically? Well, I'm looking specifically, so I'll make sure what all the things I wanted to write down on here were. This one right here, okay? So the hydrolysis of the conjugate base. Why? Because your weak acid produces a strong conjugate base, and what's going to happen? It will do this, CH3COO negative, okay, plus water. Let's show that it will pull apart some of the water and you're left with some hydroxide ions. Okay? So at the equivalence point, the pH is going to be in the basic range due to the hydrolysis of the salt that was produced. Could you quantify the extent of the hydrolysis? Yes, you can, because we know the Ka value of this weak acid is going to have a strong conjugate base because the Kw equals the Ka times the Kb, right? That was a constant. And you've got a value now for your Kb. Now, what you would do and practically in the lab is that you've got to choose an indicator that's going to change color when you need it to change color. So you're like, well, I know it's going to change color in the basic range. So what indicator changes color when it's pH of 9? How am I going to be able to see that that actually changes color if I were to do this lab? Okay, so then you look it up in a table. You're like, ooh, I've got a few indicators here. I could use thionyl blue, maybe phenolphthalein, maybe thymolphthalein. How do I know? For this one right here, you want to choose one that has the color transition when you need it, and you want it to be fairly distinct, right? So you want it to actually show a good color change Distinct between yellow and blue isn't nearly as good as between colorless and pink, so you might choose phenolphthalein in this case over the thymol blue. Does that make sense? Okay, let's do the next one. So now I've left all my notes on here, so I'll just talk your way through it, but I think you'll be able to make sense. Another option, you've got a weak acid and a weak base. You're thinking to yourself, these are going to produce strong conjugates for both of them. So what's going to happen in this case? Can you think ahead and predict what's going to happen? 5% battery, let's go. It's going to have an equivalence point, you would read this from the graph, at a pH of 7. Why is that? Weak acid, weak base produces strong conjugates, and look here. Both of those strong conjugates will pull apart water. So not only do you get excess hydrogen ions from the fact that you've got a strong acid, you're also going to get a lot of hydroxides from the fact that you've got a strong base. Both of those will produce those ions, and then you are left with a counterbalance between these two. And guess what? Your color change is going to be somewhere right at 7. Distinct color change, and you want it to change color at 7, you could choose bromothiamyl blue here as opposed to phenol red or neutral red. Don't worry again about too much of those indicators. It just basically means you just choose one that's going to change color when you want it to change color. Okay? Next option. Strong acid titrated with a weak base. Okay? Strong acid, weak conjugate base. Weak base, strong conjugate acid. So that's why I get hydrolysis of water, because of my strong conjugate acid that was formed from the weak base that was originally in my solution. It acts like an acid, is a proton donor. You're left with hydrogen ions, hydronium ions, same, left in the solution. Where's your equivalence point going to be? Acidic range. Let's see. Yep. There you go. Can you see here? You would read from the graph that was at a pH of 5, and then you would read down, what's the volume of the base that was added in? 6.00 mils. You could then take that information and then find your unknown concentration of the acid given this data. Okay? Last one is one that we use all the time, and this is why up until grade 12 you're like every time you use a strong acid and a strong base, because we always use hydrochloric acid and sodium hydroxide, you end up with a pH of 7. We're neutral because they both produce weak conjugates that do nothing to the hydrolyzation of water, and so there's no table here to show that because there is no hydrolysis of water. All right, so lots of information on this page. If you want to actually practice and you want to try to draw a titration curve, you could do that from question number 5 here, or not, right? You can just leave it as that. And believe it or not, we've covered everything for grade 12 in unit number 5. So I hope that was helpful for you, and I wish you luck next time you do your titrations, and we'll talk to you perhaps next week when we do our Google Meet. Okay, thanks for learning.